And we have focused on mainly magnetic actuation. And I'll talk about how to make magnetic actuation to create such shape programming. So our first study in this topic was starting from a very simple experiment and design problem. And I think there was a question of what is active matter is. As a roboticist, active matter is for us a microrobotic system. And that means you need to design active matter for specific tasks and function and be able to reprogram it. And that's what we do always in robotics. So first, we have goals. So let's say, we say, take an elastic sheet, which is the simplest element we can design as the morphology. And can we program its magnetic properties and inputs that will create all the desired deformations we want? This could be one, this could be n number of deformations at the same time. So that means this is a kinematic problem, so you define the desired deformations. And to do that, we basically take the elastic sheets and magnetization along the length is variable, is changing, that we want to design. And also what we design is the magnetic field inputs. In 3D, I can apply magnetic fields to this sheet that can create all the different deformations. So I will not get into the theory, but you can take these variables, magnetic field and magnetization profile, turn them into Fourier series, and then create an optimization problem so that it's a genetic algorithm approach where evolutionary algorithm will have a lot of different designs for the magnetization profile and inputs and will evolve to achieve the desired kinematics, and at the end we will have an optimized solution. It's a suboptimal solution. There is no global optimization here. So because that's how also nature works, evolution doesn't have global optimum. It's always local optimum that will make it survive. And then you go and fabricate that profile and input. You give the input. So here again, what we do is there are magnetic actuators inside the salt elastomer. So how we create them is we take a negative mold, put an elastomer first, and then we cut it with the laser and put this magnetic composite. So in this case, think about all these magnetic particles, which are hard magnetic particles, and at the beginning they are not magnetized. They are just a material with non-magnetic property, and you fill the geometry that you cut, and then you use a jig which you can 3D print and deform the sheet, which is elastic. And why do I cut the black magnetic part in different areas? Because if I want to change the magnitude of magnetization locally in the given length, I can make more material, that means more magnitude, less material, less magnitude, no material, zero magnetization. So that way you can precisely program the magnitude by the area of the black part and the orientation of the magnetization by the deformation of the jig. So it's again a solved theoretical problem, and you can fabricate it. So basically we can create anything one-dimensional in this kind of profiles that we want and optimize from the algorithm. So like, as an example, as you know, spermatozoids, their deformation is dynamic and their head is almost stationary, but the amplitude of undulation increases at the tail. So our algorithm solves, this is the evolution algorithm tells us the profile along the length should have this kind of magnetization, and then we go and fabricate it, and this is the magnetic field input with a phase difference in the x and y direction. So if you do that, this is the spinning field which is creating the undulation, and if you cut the head, and you will see that you are having a swimming robot, same as a spermatozoid. So these are fun experiments, and we have done a lot of general solutions. And next, we said, okay, these were from one-dimensional design to two-dimensional deformation. And just recently, after 3 years of work, we have solved the most complicated one is, can we start from 2D or even 3D and program 3D deformations of magnetoelastic composites? Again, here, magnetic particles are inside a soft elastomeric matrix. They are not free like most of the active matter work, but they are the ones generating the deformations by their given magnetization orientation and magnitude. So the design problem here, we took more further away. This is 2D sheets. Okay, I think the screen, yeah, it's coming back. So, and also we said we can also cut the material. We can assume that there is even no material, at some locations to achieve, again, desired deformations. In this case, they can be also dynamic. Unfortunately, this kind of problem is a huge design problem. So each voxel of the sheet now can have material or no material, can have almost a large number of magnetic profile in the sense of orientation and magnitude. Unfortunately, you cannot solve it numerically easily. What we did is we created a mass spring lattice model that will simulate the dynamics of both quadratic and dynamic deformations, and then neural networks. You need to use machine learning at this stage because computationally the problem is crazily complicated. But the good thing is with approximate surrogate models using these approximate dynamic simulation models of soft magnetic composites, we could do a lot of simulation-based training and then solve the optimal desired deformation problem. Yeah, the results are there. I will just show you some kind of example again. So for example, you want to start from a straight sheet beam and create this kind of much complex deformation. So this is, in this case, not dynamic. So again, the neural network system from the learned surrogate models finds that the profile should be like this. And as you see now, we have cuts, also pieces, to make the deformation more 3D. And then, as you see, this is the simulation and this is the experiment. And also, this is the most complicated deformation you can ever achieve, from a simple straight sheet to go to this kind of 3D deformation. And the good news is it's a solvable problem, and you see the profiles. And here we use a magnetization fabrication technique that locally we can laser heat and demagnetize the material and apply the direction and magnitude. And then at room temperature, basically, the magnetization will be frozen, so we can locally magnetize like bits or voxels precisely using a new technique that we developed. So then, again, you can start from the sheet with the given algorithm, fabricate it, and this is fixed end and applied uniform field. You will see that this is simulation, and this is the experiment showing that we can achieve these complex deformations using these machine learning-based design systems. So this is more because before we were using always human intuition, but now this is a data-driven approach using simulation. Now we can solve more general design problem. But let's go to more functional devices, and because again we are doing robotics. One big challenge in robotics has been, can we make locomotion navigation systems which have many modalities? Because as you saw, the soft animals, they can walk, they can jump, they can swim, but most of the robots just fly, just swim, just walk. So, but the good news is we can design a very simple magnetic profile. We have seen waves are very interesting in physics, and here we figure out a waveform of magnetic profile, and amplitude is all constant in this case. It is a very interesting magnetic profile. Again, magnetic particles are here inside, so what we do is when the particles are non-magnetized, we wrap them around a cylinder, very simple fabrication, then magnetize it at a very high field, and then you can control the phase difference of the wave, so you can have one wave. You can wrap multiple times. You can have double waves, triple, and even half waves. So basically, you can get this kind of wave with a phase difference by just simply wrapping and magnetizing, and when you open it, you get this profile. So this was a very exciting profile, because now, with external fields, how we can create them is electromagnetically. If you have these coils, you can induce uniform field inside the workspace where you can create the deformations. So if there's no field, the sheet is flat. We call it worm-mate. It's like worm, like robot. When you apply a small field in a specific direction, it can create a sine wave. Another direction, it will create a cosine wave. And then a higher fields, you create U-shape, V-shape. And when the deformation happens, effective magnetization totally, if it's a wave, the total is 0. But when it is deformed, total is non-zero. That means also we can apply magnetic torque on the body by the fields. So both deformation and the magnetic torque now can create a lot of fun dynamics. So that means we can now roll in the U-shape on the surfaces, solid surfaces. We can undulate, so traveling wave is possible with the sine-cosine mode. with the time kind of series. And then you can undulate like a jellyfish and swim inside the water. You can climb the water meniscus like a water beetle larvae by just shape deformation. You can climb by the capillary force. You can walk like a worm using, again, only thing changing here is the field waveform and amplitude. You can jump with the elastic energy storage, and you can still walk. And physical adaptation, as I mentioned, is very important in soft-bodied organisms. And you can see that when it comes to a constrained environment, it can adapt to the environment and change the mode and can still travel. So this is great for navigation. That was a breakthrough in robotics because that was the first time a robot can do 7 different locomotion. And even the same robot can walk and turn into a gripper, soft gripper, hold some objects, and then transport it and release it. So they have many also functions. And it's all because we can program its shape dynamically from outside. So why we have been doing this research is because one of the biggest challenges in robotics is even active matter systems. Can you put all these tiny active matter systems inside the human body, which is very narrow, filled with biofluids, which are complex fluids. The paths are very tortuous, very irregular, changing diameter and morphology, and branching. So it's one of the most complicated environments that any active system can operate. So, but the nice thing is, again, with the shape adaptation and deformation control, if you have a big gap, rolling is the best. So the wheel is discovered because it's the most energy efficient, fastest locomotion if you have enough gap. But if you are in a narrow gap, then in the planar case, you can do undulation, and I'll show you that there are different modes, which is interesting. But if you get in the cylindrical tubes, like vanes, we discovered a new mode, which is a spiral mode. I'll show you that. So, because of internet, things can happen. Right, so basically, we did a lot of simulations after this first study, because this is a multi-physics problem. So especially in the narrow gaps, we have now fluid, because we are inside the human body, so it's not air anymore. As you know, fluid dynamics, solid deformation, they are coupled. And then you have magnetic actuation also going on. So, but you can solve these things using computational fluid dynamics solutions. And now you will see that these systems are highly nonlinear. What I will do is I will create a traveling wave this way, and you will see now the same robot in different basically amplitudes. Well, if it has high amplitude, it will have surface contact. Because of friction, it will go forward. But if it is low enough amplitude at a higher frequency, it will not touch the surface. It's swimming. It's the second mode. Opposite to the wave direction, it will swim. So it's a highly nonlinear. So same robot, only changing things amplitude. If you have surface contact, you go forward, and each of them has different speed because of nonlinearities of the friction. But here, if you don't touch, this is the fastest mode. And here, amplitude was a factor, but also viscosity of the fluid will matter. So this, again, very complex physics behind this. But the good news is we can just tune the frequency here and have very diverse behavior that we could never have with linear systems. And soft systems are in that sense highly exciting. And as I mentioned, in a cylindrical tube, we discovered that the same sheet can turn into a helix, and it can have a surface contact, which will create a high friction. It can even go against the fluid flow. So there's a fluid flow here, like blood, and this robot can move against the blood flow. Here, again, it's a different mode. We call surface crawling mode in the helical, like bacteria flagellum mode. Again, highly complex physics behind it, but it's about surface friction and magnetic actuation enabling moving against fluid. Again, if you move inside the ear, you need to move in a cylindrical tube with a helical mode. You get into this narrow gap, then you need to go in the undulating mode. Swimming, again, is the fastest mode. You need to create the traveling wave, very simple to do with magnetics, and then you can get in the bigger gap and you can roll. So if you didn't have all these modes, this robot couldn't get inside this gap. So recently we also said, okay, let's make the feet sticky using some microspikes and some bioadhesive. In the GI tract, you need to climb on stomach or some 3D surface like bladder. And now the same robot can do climbing. So we are exercising different modes here. And why we care about climbing and GI tract, because there are applications inside the GI tract which are as exciting for drug delivery and some other application. Another interesting thing about intelligence is the same shape deformable object, like before it turned into soft gripper, now it can turn into a sensor. So how can a soft-bodied robot can turn into a sensor? As I mentioned, in the GI tract, we make the feet sticky so that we can climb, but also when we stick, for example, we can have a small strip of a bioadhesive on the robot by applying remote magnetic field, which is precise to control from outside. We can deform it and stick to the tissue and basically again deform it to detach, and we can measure exactly how much adhesion happens between the sticky strip and the tissue. We can also do another adhesive on the whole robot and stick to the whole tissue, create a traveling wave, change the frequency and amplitude. We can characterize the viscoelasticity of the tissue. So this is the first time a wireless soft robot can go into the stomach. Because of time, I'm not showing the whole details, can go and locally measure the tissue adhesion and stiffness just using mechanical deformation and observing it with an X-ray imaging system from outside. So in that sense, soft devices can become also a sensor itself. So, but another fun organism, because I have done a lot of bioinspiration for robotics, we have been very intrigued by these small jellyfishes. And for the first time, we could create a robotic jellyfish at the same size, same morphology. This is fluid dynamics. You can see experimentally how the fluid is deforming, because it's going down fast with a large area, going backward with a small area and slower. So this is high Reynolds number. This is not small Reynolds number. This is the wake of the fluid. And it's, again, doing exactly the same swimming dynamics and all the functions of a jellyfish robot or jellyfish for the first time. So again, how it is done is a lot of details, but this is the size scale, milliscale jellyfish, baby jellyfish, ephira. And we can replicate it with this active material is here. And then we also have passive joints and passive part where there's a directional stiffness, because when we go down, we are stiff and we are large. When we go back, we are non-stiff. The joints here are directional. There's a mechanism, and that way it can have a small area when it goes up. It has a bubble for buoyancy, and this is the real picture. Besides the navigation and swimming, it can also achieve many functions. I don't know if you ever knew, but jellyfishes catch their prey fluidically, not mechanically. So they basically grab the part here because of fluid dynamics. As you saw the swimming, basically it can trap objects and molecules and anything in the food, in the environment, fluidically, because there is an attractive zone under the umbrella of the jellyfish. So here we replicated such functions for the first time. Another challenge in experimental physics was making artificial cilia. As you know, there are a lot of theoretical works that people have known, in theory, that if you can create a metachronal wave like biological cilia, they can create very effective fluid transport and cargo transport. That's happening in our body, in our respiratory system, in our brain ventricles. The fluids are pumped because of this cilia coordination. So this is our same sheets, but you see that now with the same magnetic input, they are all doing different time deformation. How can we do that? It's very simple. As I mentioned, the phase difference trick. At the beginning, when we fabricate this waveform, you can change the phase difference by wrapping it differently. And now, one beam, for example, if you apply a field left and right, you see that the deformation, this is very low Reynolds number now, because cilia works at very low Reynolds number. Left and right, sweeping is not symmetric, so we need to be non-reciprocal, as you know. And the larger the sweeping area difference, then you have more fluidic pumping happening. So we first optimize that, and then each beam has different phase difference, and we said, okay, if all of them are synchronized, phase difference is 0 between the neighbor cilia, artificial cilia. Of course, we optimize the distance before. And you see that if you're symmetric, you are doing very small fluidic pumping and object transport. But when you are negative phase difference, antiplectic, where the theory was also saying the same, there is an optimal pumping. Again, that happens at metachronal wave, which is, as you see here, one is moving the fluid, the other is taking it, the other is taking it. There is an optimized phase difference among the neighbors at a specific phase difference will give you the best fluidic pumping. So that's exciting because first time we showed experimentally that really this artificial cilia can replicate and show the theory is correct. So this is more implementation. So we will put these cilia, they are wireless and they are milliscale into the human body. When you have cilia disease, that's a very important disease, we can now put synthetic cilia and that will help for moving your brain fluids or respiratory system fluids. So we then said, why don't we integrate sensors? Because as we talk about, intelligence can only happen if you are active only, intelligence is very limited. But you need to sense also environment. So one way to do that is integrate sensors, and we can integrate easily a piezoresistive laser-induced graphene onto the surface of the same elastic sheet with magnetic profile, and we can again make them with an array. And now, actively moving them inside the fluid, we can detect boundaries, we can detect the viscosity of the fluid, we can even find the flow sensing. So basically, same actuator can sense the environment and do a lot of interesting things as an active system, rather than just moving fluids. And we can also integrate other soft materials like hydrogels that can be responsive to stimuli in the environment, like humidity, temperature changes, and light, and many other chemicals and other stimuli. So we can do that with hydrogels, so this is a fun one. So when you interact with a human finger, because of temperature and humidity change locally, the robot can respond to the human contact. And more, of course, interestingly, we can create asymmetric structures, like inspired by these plant seeds, that we can create self-burrowing systems due to the humidity changes. This is how a seed can penetrate the ground, because at night and daytime, the humidity is highly different, so that it can basically dig inside by asymmetric structures, petal-shaped structures, and we can replicate it synthetically. So another stimuli-responsive example is we can go ahead and use even more complex soft elastomers, like liquid crystal elastomers. We heard about pneumatic structures yesterday. So we can nowadays design these asymmetric molecules in any morphology, in this case in a circle. Before it was walking like a loop shape, or basically a C shape, and in a hot water, when it goes inside, suddenly because of this liquid crystal alignment, it turns into a spiral. It changes the morphology drastically, and then you can swim like a bacterial flagellum. So these are examples of how we can create physically intelligent structures that are shape programmed and drastically reconfigure the morphology using smart materials. We can also scale them down to the cell size. We do a lot of active particles with Janus particles. We can magnetically have half coating, magnetically move them inside a 3D two-photon polymerization system into a desired location, orient it with the field, and fix it temporarily with 3D printing, and then fix another one in different orientation with, again, 3D printing, and then we can network these Janus particles together. So why is this interesting? Now we can go and basically create these networks of magnetic particles that are connected with gelatin type of salt hydrogel. Yesterday, Andreas showed these organoids. We talk about how to create physical forces. This is one of the ways. So now we can put a cell inside, and with this magnetic actuation system, we can create forces on cells and tissues that we can program as we want at complex deformations. Finally, I want to mention that we can go more complex geometries rather than sheets, rather than jellyfishes. They're all planar. We can now go fully 3D. By using robotic assembly, we can assemble magnetic, non-magnetic parts, face-to-face edge bonding techniques with elastomers, and create very complex soft machines these days. So this is really pushing the multi-material and 3D morphology. Now we can make very complex soft machines. So this is a soft tube, and each segment of the circle disc has all these magnetic profiles we designed with a phase difference of 10 degrees. This is like a biological peristalsis. Now we can induce 1 millimeter diameter peristaltic wave, just a very simple magnetic field by Holbein array. We can spin the field and create this wave so that we can transport objects and fluids, like our body. We can also make complex machines like soft capsules. We can put inside drugs. By applied high field, it will deform largely and eject the drug on demand in the right place. It can also take fluid for liquid biopsy, all enabled by 3D complex soft geometry and magnetic deformation control. Very finally, just this month it will be published in Nature, we have been pushing the complexity of these soft machines. Another complexity we have recently shown is we can in situ change the magnetic programming. Because before, in the sheet, you remember the magnetic profile we fabricate, but it's fixed. We cannot change the magnetic profile later. We need to reprogram it by offline later. But in this case, in situ, we can change it, and the trick is this. So we make these, in this case, concentric tubes. Each tube has a magnetic profile, which could be simple in this case, just horizontal, downward, upward, downward, different magnitudes. And each tube can be concentric, and we can actuate them concentrically. This can be done with tendons in robotics, so that we can, by changing the relative position of each tube, we can reconfigure the magnetic profile completely. If we do this effectively, total magnetization is 0, so the same tube suddenly turns into non-magnetic, or by having different modes, and even you can have different n number of tubes together. So depends on these relative distances, the deformations are different, the dynamics is different. This is the more general version. So you can have each of these actuatable different rods, which are actuated non-magnetically, so they have different actuation modality. And then, for example, let me show you, if you take one of these concentric tube, in traditional way, when people do these tubes, they can avoid objects because inside the human body, they want to reach some complex heart region, for example. The problem is their tip is always bent, and they cannot avoid the object obstacle. But with our technique now, we can reconfigure the magnetization, and this deformation here, we can fix it, and when you align, you see that the concentric tube comes out, and we can reach this target because this deformation stays here, doesn't move with the tip because of this new technology that we developed. And we can do the same thing with not one-point bending, but for example, for more complex objects to avoid, you can have, rather than one bending mode, you can have two fixed bending modes, as you see here, and then you can still navigate to the target this kind of ways. We can also go more 2D and 3D, again, all enabled by inside tubes that have been actuated with a different modality. Let me just move faster here. So these are all different configurations. We can get very complex deformations nowadays, as you see, and even we can go fully 3D. In the last example, the reviewers wanted more complexity. So we can now have a 3D, fully reconfiguring actuated soft structure that is enabled by this actuated magnetic rods inside. So, why are they interesting? Because again, they can go and do complex tasks. You can have even multiple of them. You can fix one, you can have other one, and you can even have 3, all actuated magnetically, but with all the concentric tubes. Just to summarize, I try to show you that soft-bodied magnetic systems enabled by the active matter inside the soft elastomer matrix can create a lot of interesting stimuli-responsive, reconfigurable, and multifunctional and multimodal behavior these days, and we can miniaturize them down to cell size. And our goal is to use them in medical applications, as I mentioned, in situ sensing of tissue behavior, delivering drugs locally, fluid biopsy, and many other things that I didn't have time to show. And we are integrating nowadays more and more complex functionality like memory, computing, decision-making, and learning physically onto these soft machines. And we are trying to show them in some clinical applications. And we are also automating learning and control, because most of the dynamics I showed you is operated by a remote user, like a doctor, not fully autonomous. By this, I'd like to thank you.